Okay, so we are recording, and what 3.1 is, it's word problems, different applications of differential equations, but now you're going to solve the differential equations too. You had I believe it was in chapter 1, a section where you were given scenarios and you had to come up with the differential equation, and that was it. Now you're going to come up with the differential equation to a word problem and then solve it also. So I'm going to try to give you guidance on 3 examples, and that should help you with your section 3.1 exercises. All right, let me let you copy this example down. Okay, so all right, so of course in Calculus 2, you're used to, like, for instance, exponential population growth. You're used to tank problems. Okay, salt coming in tank, salt coming out of a tank. What's the amount of salt in the tank? But of course, in differential equations, we go to some other applications. And in this problem, you have a vertical beam of light that passes through a transparent medium. When that happens, the rate at which the intensity I decreases is proportional to the intensity at the time t, where t represents the thickness of the medium in feet. Okay, so in clear seawater, we're given here an initial condition. In clear seawater, the intensity 3 feet below the surface is 25% of the initial intensity of the incident beam. Okay, so does this initial condition here, does this initial condition make sense?
Yeah.
Yes, it does.
Good, thank you, Justin. Yeah, I mean, if you've ever been in the ocean, if you go down, you go dive down some distance, it's going to get dark. And if you dive down more distance, it's going to get darker. That's why, the Titanic, how many have heard of the Titanic? I'm sure the ship, big ship that sank and dropped like 3 miles below, I don't know if it's 2.5 miles below the surface. Wojciech knows what I'm talking about. Andrea knows. It took like 80 years to find the Titanic, right? Because, it's dark down there, and the bottom of the ocean. So, all right. So I always like to think of real examples. So, all right. We want to find the intensity of the beam 15 feet below the surface. So what do we need to first find in order to solve this problem? What do we first need to find?
The differential equation.
That's exactly right. That's right, Michael. That's right, Justin. The differential equation. Got to find the differential equation. And how are we going to find it? Well, they're saying the rate. And when we think of rate, what do we think of in differential equations? A rate means a
derivative.
That's right. Good, everybody. A derivative. A derivative. So the rate at which the intensity decreases, so they're talking there, okay, di dt, because the intensity is a function of how far below you are from the surface of the water, the intensity of the light, di dt, okay. Now they're saying the rate is proportional to I of t. So it's proportional to the intensity itself. And what's going to go here? What has to go here in front of the I?
The constant.
Slope.
Good, a constant K. A constant K. So this is our differential equation, and this is what we need to solve. Are there any questions so far before I go to the next page? All right, now I'll make another comment too. This problem, they give an initial intensity of I sub 0. So that means that's some number, but they're letting it be like, it could be, like any number, So your final answer is going to have to be in terms of I sub 0. Okay, and WebAssign, you can type in I sub 0, right? So okay, let's go forward here. So okay, here is the initial value problem then. di dt is equal to k times I, where 3 feet below the surface, the intensity of the light is 25% the initial intensity of the beam. Okay, so we can solve for this intensity using separation of variables technique. We can solve for that intensity using that technique. Now, you've learned some multiple techniques for solving linear differential equations. You've learned separation of variables technique. You've learned the integrating factor technique. Well, I guess those are the main two, right? So this clearly, even though we could solve this problem either way, let's use separation of variables. Now, right off the bat, I'm going to ask here, I get down to here, okay, di dt equals k times I, and I'm wondering, should k be negative or positive for this problem?
It should be negative.
Negative.
Because,
Negative.
it's decreasing.
It should be negative. Very good. Very good. All right. Because the rate,
The intensity is decreasing.
there you go. That's what I'm looking for. Okay. All right. And so, okay, we're going to work it out. Oh, and I do need an integral here. Thank you. Student caught that. There should be an integral right here. Very good. And this is just a standard easy separation of variables problem. Now the antiderivative of 1 over I, normally we would put the log of the absolute value of I. But intensity is understood to be positive, so we don't need to have absolute values there. We always want to justify those kind of steps. And then we'll exponentiate both sides of this equation, and the intensity will equal a big constant C times e to the kt. All right, are there any questions so far? Okay. Zachary says the initial value is that 3 feet below the surface, the intensity is 25% of the initial intensity, I sub 0. That's your initial value. And naturally now we need to make use of that. So may I go to the next page?
Yes. It's okay.
All right. Thank you, Thomas. Here we go. So this is our solution, but again, this is a general solution. General solution. And you notice here that we have 2 unknown constants. We have our big capital C and we have our lowercase k. So since we have 2 unknown constants to solve for, we have to then make use of actually 2 initial conditions. Okay, and there actually are, because 3 feet down, the intensity of the beam is 25% the initial intensity, I sub 0, but we also know that I sub 0 is the initial intensity. So I sub 0 is equal to the intensity at time equals 0. Well, we haven't solved for k yet. We're not there. Andrew's saying, why is k not negative here? Oh, well, what'll happen is, Andrew, is I just put in a k, but that k could be a positive value or a negative value. That's all. And if everything works out right, when we solve for that little constant k, we'll get a negative value. All right, good question. Good question. Okay, so first of all, what I do is I put time, I apply this first initial condition right here, and I can solve for my big constant C, and my big constant C equals I sub 0. And then I'm going to apply my second initial condition. Let me give you a moment to catch up. Okay, so are there any, so now, you know, we know what that big constant C is, but we have to solve for little k, and I end up with this equation, 0.25 equals e to the 3k power. What are we going to do to both sides of this equation to solve for that little constant k? That's right. Good. Take the natural log of both sides. So I will, if you're good, I'll move to the next page. Well, opposite of exponentiation, Thomas, we're going to take the log of both sides. But you have the right idea. I know that you're thinking logarithmate. I don't know if that's a word, but you know. And sure enough, k will equal negative 0.4621, as we expect it to. So that's, you know, sometimes it's helpful in these kind of problems to know, to think a little bit about what a reasonable answer would be. Okay, I know in statistics it's extremely important to think about what a reasonable answer would be. So then the answer is that I of t is equal to this initial intensity, I sub 0, times e to the negative 0.4621 t. And that's what you would type in WebAssign. You would actually type that in. How many have noticed sometimes when you have to type in symbols, a calc pad comes up in WebAssign on the right that has buttons to help you type in symbols and things? How many? Yeah, so probably Zachary knows about that. So probably the calc pad would pop up on that. So then 15 feet below the surface, the intensity of the beam is going to equal 0.00098 times the initial intensity of the beam. So it's greatly diminished. How many have ever seen like divers carry flashlights with them? Underwater flashlights. Okay, Matthew knows what I'm talking about. And Christopher, and you know, so Thomas, so you know, now you have a little bit of, you have a math understanding of what's going on. So this would be what you type in WebAssign. So of course, your numbers would be different. That's right, Matthew's right. Once you get beyond a certain point, it's pitch black. And as a matter of fact, in terms of evolution, if like sea creatures that live like way down below the surface, I mean, I'm trying to recall, but I don't think some of them even have, I'm trying to think if their eyes are not fully developed. I'm not sure, but I thought I had heard of this. Okay, Zachary says a lot of them do not have eyes. Okay, well, you know, okay. All right, are we good with this problem? May I move to the next problem? Are there any questions? Okay, Kathy is good. Okay, Paige. All right, Christopher. Thank you, Andrea. Okay, let me know, Paige, when you're good. Okay, good. All right, great. All right, thank you, everyone. Well, let's move on then. Okay. All right. Here's another tank problem. We can't get away from them. You know, the tank problems. Let me give you a moment to copy this example down. Okay, so let's take a look at this problem here. In this problem, we have a tank that contains 50 pounds of salt dissolved in 300 gallons of water. And then you have a salty brine solution. It's pumped into the tank at a rate of 3 minutes. It mixes with the solution, and then the mixture's pumped out at a rate of the brine solution's pumped into the tank at a rate of 3 gallons per minute. It gets mixed up with the solution, mixes in there, and then the mixture's pumped out at a rate of 3 gallons per minute. Okay, so could the mixture be pumped out? Let me just ask. Could we pump the mixture, could we pump the brine solution in at 3 gallons per minute at that rate, and then let the mixture get pumped out at a rate of 2 gallons per minute? Would that be all right?
Well, the amount of liquid in the tank would start to increase.
And that's right. What would eventually happen?
I guess it would overflow.
It would overflow. So, there are reasons for, we can pump the fluid out at a less rate, but then of course the tank would let me see here, well, I hadn't even thought about that, but
Spill.
yeah, we just don't want it to overflow. We don't want to get sidetracked here. All right. So at this point, the amount, the fluid is steady in the tank, but in that sense. But what we want to do is we want to find the amount of salt in the tank at time t. And in this case, the concentration of salt in the inflow is variable, and it's given by this function here. Okay, the concentration inflowing of the briny solution is 2 plus the sine of t over 4 pounds per gallon. So you're kind of used to problems where, where the concentration of the briny solution coming in is a constant concentration, 2 pounds per gallon. But in this case, we have a variable concentration flowing in. And it's important to be able to deal, as engineers and scientists, we need to be able to deal with problems, that like this, because, there's no, we could have a situation where we do have a variable concentration of brine coming in. It's probably more realistic in a sense. But at any rate, let's go ahead here. What do we have to do? What do we have to do for this problem to begin? What do we need? What do we need?
Equation.
Yeah, we need that's right, Michael. We need a differential equation. So, with tank problems that you have, that the differential equation is going to be equal. Well, by the way, the differential equation in this case is going to be dA dt, right? Because we would solve that in the end, that differential equation, to find the amount of salt in the tank at time t. So this is our differential equation. And from your understanding of tank problems that the differential equation would be the difference between the rate of salt coming in
And the rate coming
minus
out.
the rate of salt going out per unit time. Question? Yep. That's right. And so the rate of salt coming in, well, the concentration is 2 plus the sine of t over 4 pounds per gallon, but it's flowing in at a rate of 3 gallons per minute. And so what happens is, as you should be aware, is this, for my units, is this right? what should the units be for dA dt? What should the units be for that derivative?
Pound per minute.
Gallons
Good.
per minute.
Pounds per minute. Because the amount of salt is measured in pounds and time is measured in minutes. And so I feel, you know, very comfortable because the units here, gallons, simplify out, and I'm left with units of pounds per minute. So you take the concentration of this brine solution coming in times the rate at which it's coming in, and that gets you pounds per minute. Similarly, for the rate of salt per unit time going outward, well, the flow rate is 3 gallons per minute, and then the concentration would be whatever the amount of salt is in the tank at time t, which is the variable A, divided by the amount of gallons in the tank, which is 300 gallons. And that gets you then A over 100 pounds per minute. And so then the dA dt is equal to the rate in minus the rate out. And so are there any questions? I'm going to let you, slow down a little bit, make sure you're comfortable, but are there any questions up to this stage here?
No, actually, I think this is one of the easiest problems we have seen, honestly. Just rate in,
Well,
rate out.
Don't
yeah,
jinx
well,
it.
of course, we haven't solved for we haven't solved for A of t, but I like hearing that from you, Thomas. I like hearing that. So now let me ask you, is this differential equation here, is it separable? Okay, Antonio's correct. It is not separable. Now wait, though, Mark has a question. Wouldn't you have to distribute the gallons per minute? Well, the gallons per minute in terms of units, Mark, the gallons per minute, the gallons simplify out when you multiply the concentration times the flow rate, and that leaves you with pounds per minute. Okay. Now, Zachary has an interesting comment here. So, hey, what's going on here? All right, so this differential equation is not separable. So for some reason, I'm writing the differential equation like this. That's right, Zachary. Why would I be writing the differential equation this way, in this form here?
To get the integration factor.
That's right, integrating factor. So I'm going to use the integrating factor approach to solve this differential equation. All right, and so may I move to the next page? All right, Thomas is good. Okay, let's move to the next page here then. Okay, so I put the differential equation in standard form, and then in front of my dependent variable A, I got 1 over 100. That's the P of t. And so my integrating factor is going to equal then e to the power 100th t. Okay, let me give you a moment to catch up here. So we're to here.
Professor,
Yes, coming. Yes, yes, yes.
can you explain what? Can you explain what's happening? I mean, on those two first lines, please. I'm not.
You mean like where the blue checks are?
Yes, yes, please.
So this is standard form
Okay.
for the integrating factor. You know the integrating factor, and I'm getting a little bit of blowback here. One moment here. So the integrating factor, this is section 2.3, is e to the integral of p of t dt. That's what I did. That's what I did. This is that's right. Matthew has it in the chat line. Mark A. So all this is a section. It's just a section 2.3 problem now. I'm going to solve this differential equation using section 2.3, integrating factor approach. And I have my integrating factor. Hold on, let me shut my email off. I don't want it disturbing us. Hold on here. Okay, one moment, class. Geez, hold on. Did I get? Yeah. So, Thomas, we can chat a little more after class about this, but this is just section 2.3 right here. Well, the whole thing's 2.3. And what we do is we multiply the standard form of the, this is the differential equation in standard form. I multiply through this differential equation by the integrating factor. Do you see here how I do that? But it's something you did on the exam. You had a few problems on the exam where you had to do this on part 2. And then on the left side, the left side of the differential equation can be expressed as d dt of the product e to the 100th t times a. If you take the differential, the derivative of this product of these two functions, e to the 100th t power times a of t, you will get, using the product rule, you will get this here. And so now I'm going to integrate both sides of this equation, and integrating the left side of the differential equation is going to give me, I'm going to be taking the integral of a derivative here, and that just gets me the function back. All right, Thomas is good, good, good. That's right, A is the amount of salt. Thank you, Michael. Are there any questions up to, well, let me give you a moment to copy, to catch up here. Okay, yes, Mark, you want me to go back to the previous page? Okay, let me go back here. Hold on, class, just for a moment. All right, Mark, is your question answered here? In the, I mean, do you have a question on this page here, or? All right, well, let's keep, all right, so hopefully, because, good, so Mark's asking why is the concentration, so the fluid, when it flows out of the tank, okay, what's its concentration? Well, it would be the amount of salt in the tank divided by the number of gallons in the tank, which is always going to be 300 gallons because you're pumping a brine solution in at 3 gallons per minute, but then you're draining the tank at 3 gallons per minute. So the concentration of salt in the tank at time t would be the amount A, and you know we of course I mean A as a function of t, the amount A divided by 300 gallons. Okay, very good question, very good question. All right, and are there any questions up to here before I move to the next page? Obviously, our challenge ahead of us is to integrate the right-hand side. Okay, that's our goal, our challenge ahead of us. All right, very good. So let's, so of course I have the integral here of a sum. The integral of a sum is the sum of the integrals. So I will, yeah, I agree. And David, on the next page, that's what we have. Very good. That's what I do. So on the right-hand side, I'm going to have the sum of two integrals. 6 times the integral of e to the 100th t power dt, and then 3 times the integral of e to the 100th t power times the sine of t over 4 dt. Of these two integrals, integral 1 and integral 2, which integral is easier to do? Integral 1 or integral 2? Integral 1, all right. How many remember integral 2 when you have like an integral of e to some power of t times the sine of t? How many remember doing that in calculus 2? That kind of problem, where you have to integrate it by parts, and then how many times do you have to integrate it? Good. Andrea remembers twice, and then you get the original integral back on the right-hand side, and then you have to add it to the left side. Thomas remembers, and then how many remember that? Calculus 2.
Now you're bringing back some memories.
All right, brings back memories. And of course, but this integral, it's going to be harder to do that with because you have, you know, sine of t over 4. That angle isn't like, you know, it isn't like you have the integral of e to the 2 theta times the sine of theta d theta. It's complicated because of the values here, you know, in your integrand. So we're going to use MATLAB. you're going to use MATLAB to integrate that second integral.
Dr. Duty, for this, that term that you just highlighted right there, is the 3 already been multiplied by this this evaluation at the bottom here, or is it only done when you do then?
Well, I'm strictly for, okay, good question. For MATLAB, what I'm doing is I'm leaving the 3 out and strictly just doing the integral of e to the 100th t times the sine of t over 4 dt.
And without the 3, that just gets you the
Without the 3. And as a matter of fact, I'll tell you what, let me show you where you can do that. So if you go into your Blackboard, and I'll actually I'll bring this back, class. I'll bring this back. Don't worry. Let me show you the program. So share application. Go into Blackboard. Okay, is everybody seeing Blackboard okay on their screens? Always like to check. Good, thank you, Kathia. All right, go to MATLAB Programs. Click here to see MATLAB Programs, and here's a new one for section 3.1. This MATLAB program will help you with integration needed for a tank mixing problem where the inflow concentration of salt is variable, not constant. So you click on the MATLAB program, it'll download it on your computer, and then if you click on that, it should open up MATLAB. I'm sure you all have MATLAB installed on your computers by now. Okay, and then hold on here, class. Let me go into the application here. Okay, so here's the code. Here's the code. So first of all, I have the clear vars command. I always like to clear out old variables, so I traditionally put that at the beginning of my programs. So I define symbolic variable t. My integrand is e to the power 100th t times sine of t over 4, and then int, integrate the function. And so what I'll do is I'll copy the code. I'll copy it. And then paste it on the command line, hit enter. So normally we do integration by hand to show we understand the techniques, but this problem, it's very complicated to do it by hand. So you use the MATLAB and you will get your answer here. And that is what is on the solution. So I'll go back to the solution. Are there any questions? Hold on here. int, Michael, it's a command that will produce an antiderivative. That's what int stands for. It stands for integral. But you have to have the sims of t and the function defined first, naturally. Question? Oh, let's see. Hubong says add pretty f at the end and it'll be, okay, let me try that. I hadn't thought about that. Hold on. Hold on. Let me see. So pretty f. Oh, wow. Oh, well, that tells me the function is pretty. Okay, so what Hubong's saying is if you use the command pretty, you could, hold on here. Let me do it like this. Let me do pretty on the integral. There we go. There we go. There we go. Okay, thank you. Thank you, Hubong. Very good. Very good. All right, let me stop there, and it's in the recording, It's in the recording. Pretty on the result. No problem. No problem. So now we'll go back to our file here. And let's see where we are. Okay, so then this here came from MATLAB. And then if you work it out, the formula for the amount is going to equal, well, what you have to do now, of course, in this equation above, you have to multiply through this equation here by the, you want, well, you can divide the equation by e to the 100th t power, or you can multiply through the equation by e to the negative 100th t power. And when you do that, this is going to be your result. So you're going to have a problem like this in your homework. So I want to go over this with you. But that constant there, okay, you still have that constant of integration that you have to solve for. So use your initial condition that initially there are 50 pounds of salt in the tank. Apply the initial condition to this equation so you can solve for C. And C will equal negative 168,400 divided by 313. And then I'll show you the final answer on the next page, but I want to make sure you're all caught up okay. Let me know if you have any questions. Let me know when you're caught up. Thank you, Michael. Michael's good.
Oh wait, so the negative 1250 over 313 e to that whole term, is that already been multiplied by 3, or does that still have to be multiplied by 3?
What I did was, okay, good. So this 3 here, I multiply it, I distribute it through. Hold on, let me clear this off. This 3 here.
Well, I know you distribute it through. I just want to know if at the step that you're at right now where you're circling it, have you done it already?
Yes, I have. Oh, I see what you mean. Hold on. No, I'm not. No, I'm glad you asked that. No, I'm not. This here is basically it's a simplification of this here. And I multiply by 3 then after. So like the 5,000, the negative 5,000, I distribute it on both terms. And that gets me this. But then I'm going to distribute the 3. I'm going to multiply 3 times all of this, and then that's going to get me this result. Good question. Okay, so let's then, if we're good, let's go to the next page here. Here's the final answer.
Actually, can you just go back a quick second?
Sure. I'm going to have one more example to do with you all.
Okay, I'm good, thank you.
You're good? All right, everybody's okay?
Yeah, I wish you can show how you distributed the 3.
I'm going to let you look at that, Thomas. There'll be a recording of this. I'll make sure it's available. It'll be under course content. So Thomas, don't worry, it's gonna be here. I'm a little pressed for time, but I'll tell you what, Thomas, can you stay a few minutes after class?
Yes, yes,
Okay,
yes.
all right. We'll go back and look at it. Not a problem. Okay, so then here's your amount. Absolutely. How many think this is a really beautiful problem? I mean, this is an engineering problem, right?
Oh,
You can handle a problem now where the rate of inflow is variable. Well, there are a lot of numbers, Matthew. There are, and fractions, but you know, all right. Sometimes, you know, in problems, you end up with fractions, and sometimes they're not too pretty, but it's okay. We can manage. If you're writing a report, you know, if you're an engineer or mathematician, statistician, and you're writing a report for somebody, they're going to want to see nice fractions, very likely, right? They might not understand math so well, but fractions really, you know, help just kind of, they're nicer than decimals, you know. Let me see, there was a question. Yes, so and for this problem, this problem, when you see it in your homework, use MATLAB for this particular problem. The other problems you should work out by hand. Your separation of variables, your integrating factor approach. But for the integration, for the integration, you know, do the integration by hand. But for this particular problem, for that, because the integration is so nasty, you should use MATLAB to help you. All right, very good, very good. All right, let's look at one more example here. Now this next example, probably what I'm going to have to do, I want to talk about the example, but I'll probably just have enough time to show you the solution, and it'll be in the recording, and you might have to refer back to the recording, but I think it's worth talking about this example. So let me give you a few moments to copy it down. In your homework, you're going to, well, yeah, in your homework, you're going to have problems also that deal with Newton's rate of cooling. They have an example. How many have heard of that? Newton's rate of cooling. And there's a differential equation for that. How many have? Okay, Matthew's seen it, and Anne's seen it. And so the book, you know, it's important. It's important in physics. That's right, Michael. So they have example 4, the cooling of a cake. So in section 3.1, so you can, they have an example of Newton's law of cooling, example 4 in section 3.1. All right, let me give you a moment to copy this.
I have one more question about the work for the exam. So do you require us to have the work in order, like number-wise, or does it matter if it's mixed up?
Well, I'd really prefer it to be in order, if possible, Christopher. But I mean, like, you know, what I think's good is having like the exam 1, part 1 work, followed by the exam 1, part 2 work, followed by the remediation part 1 work, followed by remediation.
I mean, like,
That's okay. That order's fine. Yeah.
Okay, okay. Yeah, I was gonna do that. I was wondering like the questions itself.
Oh, that's perfect. No, that's perfect. That's perfect.
Okay, because I have my questions like mixed up for each part.
Okay. Okay. Very good. Very good. And so I'll talk about this problem, but let me give you another moment. So again, for the homework that's due Sunday, you'll see some Newton's law of cooling, but problems. But again, there are some help aids on that in the homework, and you have an example in the book too. Yeah. Michael, hang out after class for a moment, okay? And I'll address that question. Okay, all right. So in this example here, harvesting, okay? How many have seen, for instance, maybe driving on the road occasionally, this might be maybe more in the country, but you've seen like big tanks. You know, you'll see like a farm, and the farm will have big tanks. Like pools, like they're like pools, but they're clearly tanks in the ground. Thomas has seen that. So, you know, fish harvesting, okay, fish harvesting. So in this case, and also you can think of harvesting like if you have like a lake, people fish in the lake, that they take fish out of the lake. That's harvesting. So in this problem, you have a differential equation. The growth rate of the population with respect to t is proportional to the population at time t. That would make sense. But then you have this minus h. So h would be your harvesting constant. H is called the harvesting constant. And there's a minus in front of that h. Why is there a minus in front of the h?
Because it reduces the population.
That's right. Good, Michael. It cuts the rate of growth goes down when you harvest fish out from the lake. And why would the rate of growth be decreased when you harvest fish out of the lake? Why would the rate of growth be decreased? There's less fish to do what?
Pair out.
What do fish do?
Mate.
What do all animals do?
Mate.
They mate, they reproduce. Good, Andre, good, Thomas. They mate, they reproduce. So if you're taking fish out of the lake, for instance, there's less that are going to reproduce. So this reproduction. So this differential equation makes perfect sense. Now, is the differential equation separable? I'm just going to ask that, and then I'm going to go to the solution and do it real quick because I know it is separable. So, well, it actually, Zachary, can be separated. Watch, look on the next page here. So I'm going to just basically show this to you. It's going to be in the recording. You're going to have to go back to the recording because our time is up. But dp dt is equal to k times p minus h. Divide both sides by k times p minus h. Okay, and then you can separate the variables. You'll make a substitution. You'll let u equal k times p minus h. And it turns out you'll have 1 over k times the log of the absolute value of u equals t plus c. This is going to be, you know, when you integrate both sides, you'll get this. You'll get this. So I'm showing you just some. It says in the example, it said determine how to solve the differential equation. So I'm giving you steps on how to solve it. You're going to get down to here, and then you're going to multiply both sides through by that little constant k, and then you'll exponentiate both sides to isolate the absolute value of u, and then you'll substitute the u in, the kp minus h. You'll substitute that in, okay, and in the end, you'll solve to get that p will equal c times e to the k-th power plus h over k. Okay, so you can see naturally the population of fish at times t is dependent on the harvest rate, okay, divided by k. All right, and then you can solve for that constant c using this information. So that initially the population is p sub 0. So I just wanted to show you how to work this kind of problem, because I know it's going to come up in the homework, and I thought a little guidance would be helpful. Are there any questions on this? And it's in the recording, right? It's in the recording. All right. If not, let me stop there. Let me stop the recording here. Let me just see. Yeah, let me stop.